Hello everyone, welcome back to my YouTube channel. Myself Monisha V, studying in Sri Venkateswara College of Engineering from the Department of Information Science and Engineering. My topic for today is the SATM system. Contents for today's topics are formulations of the system, context diagram of SATM, SATM with structure analysis, SATM terminal, entity relationship of SATM, SATM call graph. Formulations of the SATM system. The simple automatic teller machine system. There are function buttons B1, B2 and B3, a digit keypad with a cancel key, slots for printer receipts and ATM cards, and doors for deposits and cash withdrawals. The SATM system is described here in two ways, with a structured analysis approach and with an object-oriented approach. These descriptions are not complete, but they contain details sufficient to illustrate the testing techniques under discussion. This is the context diagram of the SATM. As you can see, the simple ATM system, which is being connected to the keystroke, screen, slot status, slot command, door status, and expected pin pad. And it's also connected to the central bank, terminal screen, terminal keys, terminal slots, and terminal doors. Two contents layout with smart heart. As you can see, there are three groups, Group A, Group B, and Group C. First bullet point here, second bullet point here, and third bullet point here. SATM with structured analysis. The structured analysis approach to requirements specification is the most widely used method in the world. It enjoys extensive case tool support as well as commercial training and is described in numerous texts. The technique is based on three complementary models: function, data, and control. The structured analysis approach is required to require specification is the most widely used method in the world. It enjoys extensive case tool support as well as commercial training and is described in numerous texts. The technique three complementary models are function, data, and control. This is the example of an ATM card where it has 15 screens. Where the first screen says, "Welcome, please insert your ATM card." Second one, "Please enter your PIN." Third screen says, "Your PIN is incorrect, please try again." Screen 4, "Invalid ATM card, it will be retained." Screen 5, "Select a transaction." If it is a balance, deposit, withdrawal, you can select the transactions and it will 6th screen will show you the balance amount. 7th screen shows the enter amount. Withdrawals must be multiples of $10. The open and filled arrowheads on flow arrows signify whether the flow item is simple or compound. The portions of the SATM system shown here pertain generally to the personal identification number PIN verification portion of the system. SATM terminal. The depth case tool distinguishes between simple and compound flows, where compound flows may be decomposed into other flows which may themselves be compound. The graphic appearance of this choice is that simple flows have filled arrowheads while compound flows have open arrowheads. As an example, the compound flow screen has the following decomposition. As you can see, this is the SATM terminal where it shows, "Welcome to the simple automatic teller machine. Please insert your card service." As you can choose three options, B1, B2, B3, and you can type the receipt and ID card, and there will be two options of cash dispensing drawer and deposit envelope drawer. The structured analysis approach models shown here are not complete, but they contain sufficient details to illustrate the testing techniques. The structured analysis approach to requirement specification is still widely used. It enjoys extensive case tool support. The techniques used are based on three complementary models: function, data, and control. Here we use data flow diagram for functional model, the entity relationship model for date, and finite state machine for the control aspects of SATM. As you can see, this is the data flow diagram for the SATM. The techniques are used are based on three complementary models: function, data, and control. Here we use the data flow diagram for the functional model, the entity relationship model for data, and finite state machine model for the control aspects of SATM. Entity relationship of SATM. As you can see, this is the entity ER diagram for the SATM. The customer ID PAN, and the users, and it uses the terminal ATM ID status and cash on hand, and and it will pass to occurs the transaction, which shows the time of day, amount, ATM number, and the account number, and the balance, and session as customer. The different screens are shown along with the ER diagram of the major data structure in the SATM: customer, accounts, terminals, and transactions. Upper level SATM finite state. The upper level finite state machine, which divides the system into states that correspond to stage of customer usage. Other choices are possible. For instance, we might choose states to be screen displayed. Finite state machines can be hierarchically decomposed in much time, the same way as data flow diagram can. This is the diagram for upper level SATM finite, as it shows the idle where it is being passed to the bad card and card OK. If the card is OK, I wait for pin, and if the pin is entered correctly, then it will shows the await transaction selection. If you want if you want to know the balance, deposit, or withdraw, if you want to know the balance, you should need to choose the option B3. If you need the deposit of the money, you need to choose B1. If you withdraw the money, you need to choose B2. And if it is done, then it will shows close session. Pin entry finite state machine. The decomposition of the await pin state. Here the state transactions are caused either by events at the ATM terminal or by data conditions. When a transaction occurs, a corresponding action may also occur. We choose to use screen displays as such as actions. This choice will prove to be very handy when we develop system level test cases. The function, data, and control models are the basis for design activities in the waterfall model. This is the pin entry of finite state machine of SATM. As you can see, the if the idle, then it will show the pin, right? And the second, if the pin is incorrect, it will shows a waiting second pin, right? And again, if the pin is incorrect, it will show a waiting third pin, right? Next, if the display screen S5 will show if the correct pin, a wait transaction choice. Decomposition tree of SATM system. This is the functional decomposition of the SATM system, where it consists of device sense and control, central bank communication, terminal sense and control, managed session, and the device sense control. It is divided into more subparts: load sense and control, plot sense and control. The terminal sense and control is to be divided into screen driver and key sensor, and the manage session is been subdivided into validate card, validate pin, manage transaction, and close session, and we get the digit. SATM functional decomposition tree. The decomposition tree is the basis of integration testing. It is important to remember that such a decomposition is primarily a packaging partition of the system. As software design moves into more detail, the added information, the functional decomposition tree into a unit calling graph. The unit calling graph is the directed graph in which nodes are program units and edge runs into node A to node B. Drawing a call graph do not scale up well. Both the drawings and the adjacency matrix provide insights to the tester. Node with a higher degree will be important to integration testing and paths from the main program. So the sync nodes can be used to identify contents of builds for an incremental development. This is the adjacency matrix for the SATM call graph, where it consists of 27 nodes. SATM call graph. SATM call graph is been shown in the graph as you can see in the diagram. Some of the hierarchy is observed to reduce the confusion in the drawing. Top-down integration. As you can see in the left side, there is a three subtrees, top subtree and second level subtree. At the uppermost, we will have subtree for the four components in the first level decomposition. There will be four integration sessions in each one component will be actual code and other three will be stubs. Top-down integration follows a breadth-first traversal of the function decomposition tree. Bottom-up integration. As you can see in the leftmost, there is the bottom-up integration. Bottom-up integration is a mirror image to the top-down order with the difference that stubs are replaced by driver modules that emulate units at the next level up in the tree. In bottom-up integration, we start with the leaves of the decomposition tree and test them with the specially coded drivers. There is probably less throwaway code in drivers than there is in stubs. Pairwise integration. As you can see, this is left in the left diagram. This is the pairwise integration. The idea behind pairwise integration is to eliminate the stubs driver development effort rather than develop stubs and our drivers. Why not use the actual code? At first, this sounds like a big bang integration, but we restrict a session to just a pair of unit in the call graph. The end result is that we have one integration test session for each edge in the call graph.